So far in the course, we've spoken about linear methods. What these are linear hypothesis spaces. And last week, we drilled in a little bit to how we can get kind of effective, complicated prediction functions using linear hypothesis spaces. And the technique was to engineer new features to pull out kind of interesting nonlinear effects in the original input space. And then once the feature extraction had kind of pulled out the nonlinear parts of interest, then our linear methods could construct prediction functions that were essentially nonlinear functions of the original input. The issue is that you may need to make quite a lot of features to have a kind of an effective prediction function, and that can cause computational issues. So today we're going to talk about kernel methods. Kernel methods were very popular, probably in their heyday, I don't know, almost 15 to 20 years ago. I still think they're a useful piece of your toolkit. They're not quite as dominant as they were some years ago. But one thing that kernel methods are particularly good for is they give you access to potentially huge feature spaces, in fact, even infinite dimensional feature spaces in a certain sense, and we'll talk about what we mean by that. But it allows you access to these huge feature spaces without suffering the computational cost of the matrix exploding proportional to the size of your feature space, the dimension of your feature space. All right. So let's motivate this a little bit. So as we discussed last week, we can have an input space X that's kind of raw, no assumption, no structure on it at all. So to actually work with it, we would introduce a feature map, feature extraction. We'd map from some arbitrary input X, a file, a sound file, into RD in a d-dimensional vector. And we can introduce a hypothesis space that makes explicit this featurization. So now the hypothesis space consists of prediction functions mapping from this original input X, which we make no assumptions about, into this linear transformation of the featurized version of X. So the psi of X lives in a nice d-dimensional vector space. So psi maps from the input X to D. That's our featurization. And then we have these linear combinations of the featurized vectors, so the feature vectors. So we could talk about psi mapping from X into a feature space RD, which is a proper d-dimensional Euclidean space. So this is the setting we've worked with thus far, our hypothesis space, our affine functions on some input space, or in this case, on the feature space. And we talked about a challenge like this, where we have these two classes, the two colors, and our original feature map is just x1 and x2. And there's no linear separator for these two classes. So what can we do? And what we spoke about last time was introducing an additional feature, say x1 squared plus x2 squared. And with this feature set, we can express a separator of these two regions using an affine function of this feature mapping. And we had a little video last time showing the lifting of the points in the planes or the points in 3D space where you could separate with a hyperplane. OK. So kind of the method here is we're adding the features that capture the nonlinearity that allows us to express a more complicated function in terms of an affine function of the feature space. So we're speaking about the notion of the expressivity of a hypothesis space. So if we're restricting to kind of linear functions of a feature vector, we can have this sort of picture where the outer region you could think of as the set of all possible prediction functions, linear, nonlinear, just every possible mapping from an input X to a prediction. And in that set of functions, there's a subset, which will be the set of all linear mappings of our feature space. And if we're restricting the linear mappings and we want to grow what we can represent with linear mappings, we're going to have to add new features. OK. Great. So to get the expressive hypothesis spaces we want to make kind of complicated prediction functions, we're going to need very high dimensional feature spaces. So let's do a little experiment. Suppose we're going to start with kind of d-dimensional feature vector, plus we'll throw in a bias term. So we have d plus 1 vector, d plus 1 dimensional vector. And we want to start adding in interaction terms, just like we had a quadratic term for the circular region we wanted to separate. Let's add in, imagine all monomials, so all terms of the form x1 to the p first power all the way up to xd to the p dth power, where the sum of the powers is at most m's. Those would be all the monomials with degree at most m. And suppose we wanted to add all those in as new features. So how many features will we end up with? Think about that for a second. This is kind of a combinatorics problem. Well, I'll give you the punchline, which is it's a lot. So there's something in combinatorics called the flower shop problem, which is a very kind of elegant way to think about solving this problem. You could Google it. It's fun. Anyway, the answer for the number of features is m plus d choose m. And this number grows very quickly in m and d. So for instance, if d is 40, if our original feature dimension was 40, and we want to get all monomials up to 8th degree, which is high but not huge, we're going to get 377 million features, which that's a lot to deal with especially with dense methods, where we have dense matrices, dense feature vectors, which would be the case here. What do I mean? It's not like when we add all those monomials, most of them are going to be 0. They're all going to be non-zero. So this is in general. So this is not a situation where we have sparse feature vectors like you do on the SVM homework. So this is going to be very heavy to work with. Okay. So when you think about large feature spaces, generically, there's maybe 2 issues you might be concerned about. The first is overfitting. And the second is this memory and computational cost of the huge feature vectors. So the first one, I'm not too concerned about. We have discussed regularization at length, and that's going to kind of handle the overfitting issue for us. The second issue, the time and computation, today we'll see maybe kernel methods can help in certain situations in a very elegant way. All right. So we've come close to kernel methods before, and that was when we went through the support vector machine unit. So this, you'll recall, is the original objective function for kind of a linear support vector machine. And we went through an elaborate Lagrangian duality lecture where we were able to derive the dual of this problem. And we found that they're equivalent in the sense that a solution to this dual optimization problem will give us also a solution to this primal problem. And when we looked at the form of this dual optimization problem, let's look for all the occurrences of the input vectors x. Right? You'll find that x only shows up right here. And I've wrapped them already in feature mappings for us. So it's psi of x, j, and psi of xi. And you'll see that these x's, these featureized x's, only show up in an inner product with each other. So there's no occurrence of x without it being paired with a neighbor in the form of an inner product. And this is what we'll call ready for, it's a kernelized form in a sense I'll define in a second. So a method is kernelized. We'll say an optimization problem is kernelized if all the inputs appear only inside of an inner product with some other input. Right? So this was an example. So this dual problem is already a kernelized objective function. We introduce the kernel function corresponding to a feature mapping psi and a particular inner product. And we'll write like this. So k of xy, the kernel function on a pair of inputs x and y, those come from the original input space. We'll define that equal to the inner product of the featurized versions of x and y. Right? Okay. So why are we doing this? Why did we bother to introduce k of x, y? And the answer is that it turns out you can often evaluate this kernel mapping kxy, which is just that, more directly than explicitly computing psi of x, psi of y, and then computing their inner product. Right? So this notation is suggestive of we don't have to go through psi of x and psi of y to compute that inner product. There might be a way to do it more directly. So let's give a quick example. A quadratic feature map. Our input x is a vector from x1 to xd. So our original input space is still a nice space, d-dimensional vector space. And now we make this quadratic feature map where we have the original input features, and then we have all the square terms, and then we have all the interactions between all pairs of those features. All right. So how big is this feature vector? Order of d squared, okay, dimensions. Now, let's take any two vectors in RD, the original input space, here. And here's the claim. We can define a kernel function on these two vectors, and we want it to be equal to the inner product of these feature vectors. And it turns out we can write it as simply as this. The regular inner product in the original feature space between the two vectors plus the square of that inner product. There's a short derivation. I have it in a few slides, I think, or I have a general version of it. So what's the computational cost for this inner product, which is kind of the, by definition, inner product for the kernel? How many numbers are we going to have to touch? O of. So how many entries are in phi? Order d squared. So we're going to have to do order d squared multiplies and adds to compute this. But over here, how many multiplies and adds do we need to compute this inner product? D, order d. And this is, again, order d. So with this method, order d to compute the value of this kernel. With the kind of more naive approach, order d squared. That's a massive difference. That's a massive computational speed up. So what might have been computationally prohibitive if d is already very large to introduce all interaction terms, now we can do it rather efficiently if we can make use of this kernel trick. Okay. Any questions on this? All right. So far I'm just making this point that sometimes you can directly evaluate an inner product between this high-dimensional feature space, in this high-dimensional feature space, with some other function of the original inputs. Okay? Skipping the feature map entirely. All right. So how should we think about this k? I find it's useful to, in most situations, to think of it as like a similarity map, a similarity function. It's not like a mathematically precise statement. Precisely, we'll find that we'll take our kernels to be inner products, but in most situations, intuitively, and for the kernels that people usually use, it's similarity score is a reasonable way to think about it. Many ways to make a similarity score. We're going to be restricting to a particular way, which are called Mercer kernels, which are kernels that correspond to inner products in some feature space, which gives us a lot of mathematical benefits. All right, so what are the benefits of kernelization? One is computational, along the lines I mentioned already. Another is that we'll find it gives us access, in a certain sense, to infinite dimensional feature spaces, which is pretty interesting. And we'll come to that later in the lecture. It also, you can, if you like, you can start thinking in terms of similarities, thinking about how would I like to evaluate the similarity between two inputs from the input space, rather than thinking explicitly about what's a good featurization of the input. Right? It's an alternative way to think about it. Usually, you have your input, and you say, how do I extract the useful features? And I make a feature vector. This will give us an alternative approach where you say, all right, here are two inputs. How am I going to score the similarity? Right? And it allows us to work with kind of similarity scores rather than feature vectors directly. All right. So let's look at this SVM again. So I dropped the feature map to make it look exactly like the SVM we had originally. This is the dual form. So now we have this just xj transpose xi. Those are the inner products between two inputs. And what we can do is every occurrence of this inner product, which is only one in this case, we can replace it with the kernel function, k xj xi. Right? So if we do that, then we've essentially defined k xj xi to be xj transpose xi, which is the first kernel that we're going to talk about, the linear kernel. So in the linear kernel, we have some input space, RD, and we'll say our feature mapping is just the identity, and it maps to RD. With the standard inner product, we define the linear kernel to be just the inner product of the two vectors. Right? Very, very elementary. So this would be the kernel that we can plug in here, and it'll be exactly equivalent. And what we're headed with this is that once we have put the kernel into this formulation, we can swap out and put another kernel in, and nothing changes computationally. So that's what we're looking at here. So if we wanted to actually work with kernels, it's usually makes things much easier to introduce what's called the kernel matrix. So if we look at the SVM formulation, so if we're going to replace xj transpose xi by k xj xi, so we'll only ever need to access, at least in this optimization problem, the evaluations of this kernel function on all n squared combinations of points of x, right? Because we're only evaluating k at xi's and xj's for xi and xj being some of our input points, our n training points. So we can write down all of the evaluations of the kernel function that we're ever going to need in what's called a kernel matrix or a gram matrix. So this capital K for the kernel matrix is this matrix of all the possible inner products between our n inputs. All right? So if we're using the standard inner product, let's convince ourselves that we can write this kernel matrix as x transpose. So let's remind, what's the name we've given for capital X? Yeah, X is the design matrix. Let's remind ourselves what that looks like. So here's X. And X has the input vectors in rows or columns. In rows. That's the standard formatting. So what's the dimension of this matrix then? Yeah, n by d. We can leave off the, let's just call it n by d. OK, great. So that's x. So what's xx transpose then? Well, the product is n cross n. This is, of course, d cross m. And what's an entry of this matrix look like? Suppose the ij, this is x transpose. And then What's the ijth entry of this XX transpose matrix? Say again? Okay, so, right. If we want the ijth entry, we take the ith row, which is little xi, and the jth column, which is xj. And we're taking their inner product. Or in our usual notation where vectors are column vectors, we would write this xi transpose xj. All right. Okay, so what we've shown here is that the ijth entry of XX transpose is the inner product between xi and xj. Okay. So K is XX transpose. That's good. Do you remember in ridge regression there was a matrix that showed up? It was like XX transpose, but it wasn't XX transpose. It was X transpose X. That's right. What's the dimension of X transpose X?
D squared.
D by D. XX transpose M by N. So you'd prefer to work with the smaller one, right? So that's something to keep an eye out for. So if in kernel methods, we're going to be working with this kernel matrix XX transpose, that's M by N. And in the original space, if it's like ridge regression or something, it's D by D. So we're going to be interested in kernel methods when N is a lot bigger than D. No, N is a lot smaller than D, because we're going to prefer to work with the smaller matrix. All right. So we've defined this kernel matrix, and now we'll just plug it in. Before we had K, Ji, now we can just do the matrix K sub Ji. Because we defined the matrix to have exactly what we need. So what's cool is that, yes, here we've defined K to be XX transpose, this matrix. But we can invent some new featurization and some new inner product and make a new kernel matrix that expresses all the kind of kernel evaluations for the new feature vector and the new inner product, and take that matrix, it's the same size, it's still N by N, and swap it out for this original kernel matrix, and we can run the exact same algorithm, and what you end up with is a result that's as though you had used that full feature vector and this new inner product on that feature vector from the beginning. Okay. All right, so if we're going to talk about replacing this basic inner product, this basic kernel function with some new kernel function, let's take a little bit of a look at what might be available to us. There's a whole industry of making new and interesting kernels to capture different types of input spaces, strings and trees and graphs. And yeah, some are still used today even, but the basics get you pretty far. So here's the quadratic kernel generalized to, I think we already spoke about this one, actually. All right. Polynomial kernel. This is something that might help us with our original question. So if we define our kernel in this way, the mth power of 1 plus the inner product of w and x corresponds to a feature map with all monomials up to degree m, which is good. That's what we were talking about earlier. We said there's like 300 million of those monomials. And here we have a kernel function that corresponds to that feature map. I will say just one thing, one caveat, that this feature map, in that feature map, the monomials have different coefficients than 1, right? So when we made our featurization with all interactions, each feature was just the interactions of the x. The feature map corresponding to this kernel has different coefficients on those monomials. Just like for the quadratic, the square root of 2 is snuck in there, right? The square root of 2 snuck in there. Or there's a lot more of that going on in the feature map for this kernel. And I mention that because we're now in a position to understand why that's relevant. If we're putting different coefficients on different entries of our feature vector, imagine compared to not having them at all, what effect might that have in our modeling? Say again?
Regularization.
Yeah, it interacts with regularization, exactly. So if the feature map on a particular monomial has a very large coefficient on that feature, how does that interact with the regularization? So if it's a large coefficient, you want to go for it? Large coefficient, it makes that feature value large. Okay. So if the feature value is large, you need very small parameters to make good use of it. And small parameters are very cheap when under regularization. So the coefficients that are really large, the features, the monomials that get large coefficient in the feature mapping will be less expensive to use than ones that get small ones. So it's going to favor coefficients, kind of the larger coefficients. Okay. Of course, this interacts with the size of the feature itself without the coefficients. So maybe when you have higher, maybe the larger coefficients correspond to if x's are, say, less than 1 or something, and you have higher order terms, maybe they are anyway smaller. But the point is there's some subtlety here. And it's, while the feature map is kind of, is all the monomials up to m, we now understand that the coefficients are relevant as well. Okay. So here's the kernel that by far is most used after a linear kernel. It's called the radial basis function, or the Gaussian kernel. And it has this form. Sigma squared is known as the bandwidth parameter. Do we see why this might be called a similarity score? So what happens when w and x are equal? It's 1. And if w and x are very far apart, then this norm is large. E to the negative something large is very small. This thing goes towards 0. So at least for w and x very far apart, that's close to 0. And when they're equal, it's 1. All right, so roughly speaking, we see that it corresponds to our intuition of what a similarity measure would be. And why is it radial? Well, it's certainly independent of orientation. If you fix a w, then all the x's at the same distance have the same similarity score, kernel score. Okay, and then the question is, so with this kernel, are we still in the world of this kernel is just an inner product of a feature vector, like we were on the previous one? So is there a feature vector that corresponds to this particular kernel?
When the feature vector probably has to do something like exponent the features, right? The various features, then potentially make it.
Well, so there's a vote for, it seems possible. It's going to have some exponentiation in it. Yeah. So
you can take the integral of this kernel, which is sort of like a summation. It's, I guess, supposedly can become a closed form equation.
okay, so this is almost the Gaussian density function. So this thing is, yeah, you can integrate it. I don't know if that's going to help us get a feature vector, though. Because what we need is to write, so the question is, can we write kwx, which is e to the, right, it's got that form. Can we write that as for some phi and some inner product? So it turns out, kind of, is the answer. It turns out you can, but you need infinite dimensional feature vector, for which you're going to have to define some feature product that works in that space. So this is actually perhaps the major selling point of kernels, which is that we can handle the equivalent of an infinite dimensional feature space with our kernel method. Why? What's the dimension of our kernel matrix? It's still n by n. N is the number of data points you have. There's no dependence on D, the dimension of your feature space. So that's kind of the lovely part of kernelization. And we'll see what prediction functions using this infinite dimensional feature space look like later on. Okay. So let me just give a kind of an overview of this thing that people call the kernel trick. We've spoken around it. So we start with a kernelized machine learning algorithm. Remember, that's where every reference to an element of the input space X is encapsulated in something like this. It's featureized, and then it's only showing up in a pair with a friend with another input vector, featureized input vector, inside of an inner product. There's no raw kind of phi x transpose W or something. This does not show up in a kernelization because it's not in an inner product with another input vector. All right. So that's kernelized ML algorithm. So given one of those, we can take the inner product that shows up, swap it out with a new kernel function. The new kernel may correspond to some really high dimensional feature space, possibly even infinite. But nevertheless, once we compute that n by n kernel matrix, which the computational cost depends on n, right? We can just swap in that kernel matrix, and algorithmically nothing changes, but we do get a new result. We get a result corresponding to the new high dimensional feature space. All right. And this swap of the linear kernel for this new kernel, that's called the kernel trick. All right. So any questions on this development so far? So here's what's coming next. What's coming next is we're going to study some techniques for kernelization. So if someone presents you with an objective function, to get the SVM in the dual form, that took a lot of work. We had to learn Lagrangian duality and then go through this whole process. I skipped most of the steps, this process of deriving the SVM dual, and then it just so happened that it had the right form. It had the kernelized form, which was very nice. But in general, if we look at ridge regression, how do you kernelize that? Will this dual approach help? It's like, where do you start? So it turns out that there's a very simple recipe for kernelization in a large number of settings. And so that's our next step. It's based on something called the representer theorem, which used to seem like a big deal, but these days we see it as just a consequence of basic linear algebra. And so we'll go through that theorem, the representer theorem, and then we'll apply it to kind of the familiar objective functions we've talked about so far, ridge regression and SVM. And then the last thing we'll do is talk about how to make new kernels from old ones and how to piece together kernels that you might want to use for your task. All right, so to get to the representer theorem, we need to review what's essentially basic linear algebra, inner product spaces. But we're going to call them Hilbert spaces, and we're going to make that little caveat of the difference between a Hilbert space and the kind of finite dimensional inner product spaces that we're used to. And the only reason we need to talk about Hilbert spaces is because we want to be able to allow for that infinite dimensional feature vector, which is kind of maybe one of the more exciting parts about kernel methods, because we can use this RBF kernel, which turns out to be quite useful. Sorry?
Can I ask a question about just kernel?
Yeah, sure.
I'm a little confused about what the optimization problem is now in a space.
Okay. All right. So far, all we've done is this. We've started this original support vector machine optimization problem. And then through 2 hours of lecture, we derived this equivalent form, which is the dual. And we notice that this is kernelized in the sense that the inputs only show up in these inner product pairs with other inputs.
So we're trying to make calculating that some less expensive.
So, yes, exactly. So the cost of this, naively, is proportional to how big this feature vector is. Right. Imagine we had an efficient way to calculate each entry, each of these inner products. All right. So All right, fine. So we have an efficient way to calculate those. How many of them are there? They're n squared for all pairs of these input vectors x. So if we have an efficient way to calculate all n squared of those inner products, so that would constitute our kernel matrix. And then we solve this optimization problem, and we can go back to what would be the original solution here using the correspondence between these two problems. After this representative theorem, it'll be much easier to get a equivalent problem, and it will be much closer to this in form. Yeah?
So then, using kernelization, we are basically solving the dual problem, basically?
So are we solving, in this situation, the dual is kernelized. I don't want to say that in general. It's a different approach rather than taking the dual. Yeah. There's different ways to get a kernelized form. The dimension of?
Of the weight. After you're done with this alpha, you can convert it to the weight, right?
So the dimension of the weight vector is d, which is the dimensional of the feature space.
This is your kernel trick. Now, when you do the kernel, you convert this to.
OK, so let's work it through. So in this problem, what's the dimension of alpha? N. Alpha is n. N is the number of training points we have. OK. There's some formula, which I didn't write down here, which allows us to map from alpha back to w. W is of dimension d. The way I've written it here, d is the dimension of our feature vector.
So let's say there's a new data point. We're going to do prediction, right? Now we're going to fit into Now, do we have to use the kernel function?
I mean, this is a great question. In some sense, so the question is, OK, what do we do with a new input, x? How are we going to make a prediction with the kernel? It's not resolved yet. We're going to come to that. But that is the right question to ask. How do I make predictions? So first will be, how do we kernelize it? Then it's, how do we solve the kernelized version? And how do we make new predictions on new things? Yeah. Any more questions? All right. Let's review some basic linear algebra, some things about projections. All right. So in inner product space, over reals, it's a vector space V. We'll write the inner product this way. An inner product takes pairs of two vectors in the space and produces a real number. And inner products have these properties. They're symmetric. They are linear. And importantly, they have this positive definite property, which says that if you take a vector and you inner product it with itself, the result needs to be non-negative. And the definite part is that it's only 0. It's 0 if and only if x is 0. Okay? So we're going to use this to make a nice norm. So for an inner product space, we can define a norm on the space. And the norm tells you how big a vector is as the square root of the inner product of the vector with itself. And because of the positive definite properties, this will have properties that you expect of a norm. So for example, with the standard linear inner product, the norm is the square root of x transposed with itself. All right. So here's a question. What norms can you get from an inner product space, from inner products? So if someone just gave you a norm, how do you know whether that can be derived from an inner product? And this will be relevant to us shortly. So it turns out there's something called the parallelogram law, which is that a norm can be generated by an inner product if and only if it obeys this property, which you can write just in terms of the norm. And if it obeys this property, then you can kind of reverse engineer the inner product that gives rise to the norm with this formula. And the reason I mention this is because there are certain norms that we know and love that unfortunately we can't use as kind of corresponding to an inner product. And the example is the L1 norm. It gives us lasso. So you can kind of work out, say as an exercise, that the L1 norm is not generated by the inner product. So if you take the L1 norm, it won't obey this property. And so you can't derive an inner product that gives rise to it. The theory we're going to develop only applies to situations where the norm that you're using is derived from an inner product. So it won't help us with L1, but it'll help us with L2. Okay. So Pythagorean theorem. If two vectors are orthogonal, their inner product is 0. And we're going to denote that with that perpendicular line marker. And we'll say that a vector is orthogonal to a set if it's orthogonal to all the vectors in that set. Fine, intuitive. Now the theorem, if x and y are orthogonal, then the sum of those vectors has a norm squared. That's the sum of the norm squares of the individual vectors in the sum. And let's prove that very easily. We start with the norm squared. We expand that out into the inner product with itself. By linearity, we can expand that out. And then, of course, we're dropping. So what do we know about x and y?
The inner product is 0.
They're orthogonal. So the inner product is 0, so these terms drop out. So it's just the sum of the squares of the norms. Great. Little exercise. All right. So now let's talk about projections. There's basically two things we need to know for the representative theorem. One is this simple thing, Pythagorean theorem, and the other has to do with projections. All right, so projection. I think the working definition in your head of a projection is onto a subspace, which you should picture as a line or a hyperplane, where a subspace is a hyperplane. I picture it as a hyperplane through the origin, geometrically. Right? Subspaces go through the origin. So projection of x onto this subspace this captures it well. Think of it as the point on the subspace that's closest to x. Right? How would we define close if we wanted to make it formal? In terms of, distance, but we haven't set up a distance on this space yet. We don't have distance in our structure yet. We have an inner product and we have a norm. So what would you do? Yeah, just the norm of the difference between x and m0. That's our distance. Okay. All right, this is just our rough definition. So in math, we want the projection m0 to be closer to x than any other m that's in the subspace M. And we'll give a formal definition in a bit. But so here's the thing. We know projection exists for all the finite dimensional inner product spaces that we're used to. But we're going to want to have access to infinite dimensional inner product spaces. And we need to do projections in those spaces. So we're going to need just a little bit more. There's this condition called completeness, and you really don't need to worry about the details. I just leave it in for completeness. So a space is complete if all Cauchy sequences converge. You might have learned about Cauchy sequences in a real analysis class or something like that. So a Hilbert space is a complete inner product space. It's any inner product space, which we already defined, and it has to be complete, so all the Cauchy sequences converge. Anytime you see a Hilbert space, you can replace that in your head with RD and the standard inner product. And all the intuition goes through. All right. Precisely because we have this condition of completeness, which makes it a nice, gives us the existence of projections and stuff like that. Next slide. But any finite dimensional inner product space is a Hilbert space. So the projection theorem So it basically tells us that projections are unique, that they exist, and that they have the properties that we kind of claimed here heuristically. So if H is a Hilbert space, and that of course includes the standard inner product spaces, M is some closed subspace of H. Again, you should picture a hyperplane through the origin. Then for any point in the space, there's a unique M0, which we'll call our projection onto the subspace M, for which M0 is closer to X than any other point in M. All right? So it's called the orthogonal projection of X onto the subspace M. And moreover, and this is an important characterization that we'll use, the projection, where M0 in M is the projection if and only if the vector from the projection M0 back to X, here, so this is the vector to M0, and X minus M0 is this vector. If these two vectors are orthogonal, which of course means X minus M0 and M0 have inner product of 0. Okay. All right. So this characterizes the projection of X. If we can find some M in this subspace that has this characteristic, that the difference between X and M0 is, rather the inner product is 0, then that is the inner product. And that is the projection. Sorry. All right. So projections exist. They minimize the distance to the subspace. And the residual, you could think of this as the residual vector from X, between X and its projection, is orthogonal to the projection. So from that, we can get a very useful little corollary, which is that when you project a point down to some subspace, and you look at the norm of the original vector and compare that to the norm of the projected vector, the norm is always less or equal to for the projection. So projection reduces the norm. All right? This is very straightforward to demonstrate. Start with X. Let's expand it into the sum of the two components, M0 plus, this is X minus M0. Right? So M0 and minus M0 cancel each other out, nothing going on there. But now we've taken M0 to be the projection of X onto the subspace. So what do we know about X minus M0 and M0? They're orthogonal, so their inner product is 0. Great. So here's the squared norm. Let's rewrite that as the inner product of this thing with itself. Right? Well, that would be rederiving the Pythagorean theorem. I guess we can just use the Pythagorean theorem directly. So since M0 and X minus M0 are orthogonal, we have this Pythagorean theorem. So we could break that norm up. And then we could just drop this piece. So we arrange. If we drop this piece, we know that M0 squared must be less than or equal to X squared, which gives the result. OK. All right. So this is the other theorem that we're going to need to use. Projection reduces norm. All right. So what is this representative theorem I've been talking about? So let's go back again to our SVM objective function. And what I'm going to do is I'm going to write down a new objective function, a more general objective function, which hopefully makes things look simpler. And we'll derive some result for this very general objective function, for which this is a special case. So let's just write down the more general form, and then we'll see how it's a special case. So the generalized objective. There's still kind of this norm, this regularization piece, R for regularization. And then there's this loss piece, L for loss. And you'll note that we've generalized the 1/2 norm of W squared to just some arbitrary, some function of the norm of W. And over here, what we've done is we've noted that the X's and the W's only show up in these inner products. And so we've relaxed the form of this. This is the empirical loss, the empirical risk with this loss function. So we've generalized this to be an arbitrary function L of all of these inner products that show up here. Okay, just so this is not totally abstract, what would this inner product be? W psi of x1 in the development we've had so far. Inner product W psi of x1. This is actually should be familiar.
It's your prediction.
It's our prediction. That's right. We have these linear models. They're linear in the feature space. W psi of x1 inner product. That is our prediction function, right? F of x is equal to W transpose x, right? This is the slight generalization of that with the feature vector. Good. So yeah. So this is a very general form where L is some function of the predictions, where each prediction is given by this inner product. So we're restricting to linear methods here. Okay. And the only other tweak we made here is that instead of W and RD, we've now snuck in this generalization that W is in some abstract Hilbert space in case we want to allow for kind of infinite dimensional W's and infinite dimensional feature vectors. Yeah?
So in W transpose X, we get blocked output wiring, and so each of the W transpose X I corresponds to Y I.
Yeah.
In this case, after the transformation, is the output vector also transformed?
Okay. So let me write down what you're saying just to get it down. So in the simplest version, our prediction f of x is W transpose x. When we apply it as we are here to particular training input vectors, that would be like f of xi is equal to W transpose xi. But here we've written it in the slightly more general form where we are allowing some featurization and potentially a more general inner product. So we can actually write that as f of xi equals inner product of W psi of xi. Okay. Now, your question was, say it again?
I guess, okay, so transforming xi, the output function.
Oh, right. So the question, right. So the question is, if we're transforming x, does that in some way transform the output? And no, I wouldn't think about it as transforming the output. It's just, think of psi of xi as just giving us potentially richer feature space. Or it's like making the features for you from the input x. And then we're just back into our usual kind of linear prediction function setting. Yeah?
Does the subspace M has to be always a linear subspace for the definition of projection?
Yeah, so you can define projections onto sets. Convex sets are the easiest. But this theorem is about projecting onto subspaces. Yeah. All right. OK. So I just want to make sure you guys see that this, because this is the general form we'll be working with for a bit. You can see that this is a special case of this. And the caveats I want to have are this R function is non-decreasing. And this L, the loss term, that really is arbitrary function of the predictions. OK. All right. I've rewritten with some more details, but I think we've covered them all. The one thing we need to make explicit is that the norm that shows up here, that has to be the norm that corresponds to this inner product here. Remember, there's this correspondence between norms and inner products, and those have to be related in this usual way. OK. Great. So I'm claiming that this is a generalized linear objective function. Do we see why this is linear? Well, the linear piece are these inner products, right? So if we think of that as a generalization of W transpose Xi or W transpose psi of Xi, we're saying that the predictions are linear in this feature vector. Okay. Inner product is linear, so linear on that feature vector. All right. So ridge regression and SVM are both of this form. Is lasso of this form? No. So that's the point I was making earlier, that if you wanted to put the L1 norm here, there's no inner product that corresponds to it. So it's not of this form. Okay, but the other things we've talked about are. All right, what if we, so our ridge regression penalizes with the, actually with the square of the L2 norm, remember? So what if we wanted to penalize with just the L2 norm, not the square of the L2 norm? Is that legit? Does that fit into our generalized objective form here? Some yes nods, I see. So yes, so let's take this to be the standard inner product. So we get an L2 norm, and whereas for the standard ridge regression objective, R would square the norm and maybe divide by 2 or multiply by lambda or something. You don't have to. You could decide not to square that norm, and it still has that form. R would just be lambda times its argument. So we don't have to use the square on the norm to be of this form. So we have a little more variety than we've had so far. Okay. All right. So here's the theorem. It looks heavy, but it's actually light. Everything that I've written here is just restating what I've already said to set up the problem about R being non-decreasing, L is arbitrary, the norm corresponds to the inner product. The key result is quite concise and quite interesting. So if this objective function has a minimizer, then the form of the minimizer is very specific. The form of the minimizer, W star, is a linear combination of the psi xi's. It's a linear combination of the featurized input vectors. Does that sound familiar at all? Remember in support vector machines, we came to a point where we said, oh, look, W star is in the span of the data. All right? So this is, again, what we mean by span of the data. You have your input vectors, x1 through xm. We are featurizing them, yes, to get them into a nice Euclidean vector space. And then W star is just a linear combination of those vectors. Is that obvious? Depends how comfortable and fluent you are in linear algebra. I would say that it was certainly not obvious to me the first many times I saw this. I thought that was quite amazing. But what you'll see is that the proof to this is so short that you might eventually start seeing it in your head, and that this will be, yeah, of course, yeah, of course that's obvious, that sort of thing, yeah.
In the previous objective function, why did you say it is linear? Because psi of xi can be a non-linear function.
Yeah, so why do I say it's linear? So it's linear in the feature vector. The predictions are linear in the feature vector. So the predictions are inner product of W and psi xi. So so the predictions are, W1 psi xi 1 plus, this is linear combinations of the elements of this vector. So. Okay. Great. So anyone have a sense of how this, what might be going on here? Why might this be the case? Let me give you a little structure first. Suppose you had some W that purports to minimize, or may actually minimize J of W. And it's not in this linear combination form. Now, one way to formulate W star being in this form is to say W star is in the subspace spanned by these vectors psi of xi. Right? So we can call that subspace M. It's conveniently already written here. And let's imagine that so we're imagining that there's some W star here and, that minimizes the objective function. And then let's define this subspace M to be the span of these vectors, psi xi. Right? The span is a set of all linear combinations of these things. So we'll write this as this line here. All right. So the theorem is going to go, the proof is going to go like this. We start from some purported minimizer of JW. And then we think about projecting JW down into M. Right? So if we use the notation of last time, it's M0. I think here I call it W. OK. So let me change the notation to W. So projections exist, so we can say, all right, W is equal to the projection of W star onto M. All right. Now, what happens if we try out W in this objective function? So we plug in W. So first of all, what about the norm? We started with W star, and we replace it with W, which is the projection of W star into M. What happens? What's the norm of W star compared to the norm of W?
It's bigger.
Yeah, the norm of W star is larger because projections reduce norm. All right, that was one of our theorems following on the Pythagorean theorem. So in the first term, if we replace W star by W, the norm is going to decrease or stay the same. Stay the same if W star is already in the projection. All right, what about these pieces? So if we start with W star inner producted with psi of xi, and we replace it with W, what would happen?
It's equal.
You think it's equal? Let's write it out. All right, what do you have in mind? How would you approach this? W star, let's pick a particular one, psi of xi.
So it's equal to the input product of W plus W star minus, W plus W star minus W.
Yeah, so let's break it down into the component pieces. So we can write W star as W plus W star minus W. This is one of those trivial no-ops, right? Because W and minus W cancel each other out. But then you do the regrouping. So this is W star minus W and W. So this is W star minus W, and this is W. And what do we know about those two vectors? They're orthogonal. OK. Great. Let's do the linearity. That was actually irrelevant to this here. So let's do the linearity first. All right. So when we had projections, there's a particular thing I pointed out that was a characterization of the projection. We said, if W is in M, we'll know it's a projection if something happens. What was it? There may be two. One is that W has to be the closest element to W star in M. But there's another thing. Say again?
W and W star have the same norm.
W and W star have the same norm only if W star lives in M. So if only, basically if they're the same point. had to do with the residual vector, w star minus w.
Well, can you
Equation as well.
Great. So this, if we change our notation to the current notation, says that the residual vector, the difference between the original vector and its projection, must be orthogonal to the subspace that you're projecting into. So w star minus w is orthogonal to, let's just say, x for all x in the subspace M. Right? It's orthogonal to everything in that subspace. Okay. In particular, it's orthogonal to w. In this case, our subspace is the span of all these vectors, all the psi's. So w star minus w is orthogonal to psi of xi, because psi of xi is in M by definition. M is the span of all the psi of xi's. So this piece is 0. Why again? Because w is the projection, so the residual w star minus w is orthogonal to everything in the space you're projecting into. So w star psi xi is equal to, the inner product of w star psi xi is equal to the inner product of w, the projection of w star down into M, and wxi. So what's that tell us? These two are equal. So that means we start with w star. We found its projection w. If we swap out w star for w here, this thing only decreases, yeah. If we swap out w star for w here, what happens to the inner product?
No change.
No change, exactly. So that's the proof. For any w star, suppose it's not in this form, we can find another w that is in the span, because it's the projection into this space, that has a smaller or equal objective value. All right. So that proves this. If JW has a minimizer, then it has a minimizer of this form. All right. It may have another minimizer not of this form. Okay? That's possible. But it's only possible if R is not strictly increasing. If R is strictly increasing, then all the minimizers have this form. We haven't proved that yet. That'll be a little bit of a tweak on this proof. And you can kind of walk through it. I'll put it in the homework as something you can walk through. It's almost the exact same proof. You just have to be careful with that case. All right, and all the steps fit on one slide if you want to rehearse that. Very nice. I want to dwell a little bit more on this w star is in the span of the data, just so we get a good sense for the import of this before we go on to the next topic. So let's unpack this a little bit. Remember psi, that's our featurization thing. Psi maps generically from some input space x to RD. RD is our feature space, d-dimensional feature space. Then the conclusion of the theorem is that the minimizer of this objective function has this particular form. W star is in the span of psi xi's, right? So each of these psi xi's, think of that as a vector. What space does this vector live in?
RD.
Say again?
RD.
Sure enough, it lives in RD. That's right. Great. And then we're taking a linear combination of how many of these vectors in RD?
N.
N, that's right. Summing, we have n vectors, psi x1 through psi xn. And the coefficients form a vector themselves. Alpha, what space does that live in? Correct, Rn. Okay. Great. Let's think back to the first example we had today, where we wanted to start with this d-dimensional, d plus 1 dimensional vector, and then add in all monomials of order up to m, remember? And we said that that would have dimension like 300 million or something, right? Okay, so in this setting, what's 300 million? D, yeah, that's right. So in this notation, the huge number, 300 million, that's like D, the dimension of our feature space. And in any typical problem, n is going to be a lot smaller than 300 million. Call it 100,000 or something. So in that scenario, n is a lot less than D. Say D is like 300 million, n is like, say, just 100K or something like that. All right. So we're searching for a W star. What's the dimension of W star then in this giant feature space? Giant, 300 million. So W star is huge. We're searching potentially in this massive 300 million dimensional feature space for a W, the solution to our ridge regression optimization problem, for example. But this representative theorem tells us something very interesting about W star. It tells us that even though W star lives in this huge feature space RD, it actually lives in a relatively small dimensionally subspace of that feature space. W lives in the span of only n vectors. So W lives in this 100,000 dimensional subspace of this 300 million dimensional space. So even though initially it's like, oh, we have 300 million kind of free parameters to optimize over for W star, actually, you only have 100,000 parameters to find, the alphas. You don't have to search over the whole space. You only have to search over the thin subspace spanned by the data, by the psi xi's. Ponder that for a moment. Any questions? All right. So we'll keep this on the board while we do the next piece. All right. So we're going to use the representative theorem now to kernelize some objective functions. And there's a bunch of pieces, as was asked earlier. We've got to figure out how to make predictions in a way that's kernelized. Because, oh, here's an issue. So I made this big claim that one thing that's exciting about kernel methods is that you can deal with huge feature spaces, even including infinite dimensional feature spaces, right? OK. So let's pretend we're there already. We're using an infinite dimensional feature space. OK. So what dimension is W? Yeah, OK. So if our feature space is infinite, then W is infinite. So how are we going to make a prediction? That's the inner product of W star psi x for a new x. That's our prediction, right? Well, that's great. But this is an infinite dimensional inner product. Naively, that will take a long time to compute, right? So we are going to need to find, if we want to use these infinite dimensional feature vectors, we're going to actually need a way around computing this inner product. We're going to need a way to write this where we don't have any direct exposure to infinite dimensional feature vectors, just like we had the kernel matrix to get around it when it's like psi x with psi x prime. If these are infinite dimensional, we're OK as long as we have the kernel matrix, right? It's just k x I prime. And if we know how to compute the kernel, we're good. But here, we don't know. The kernel doesn't help us directly with this. We don't know how to plug W star into and make it like a psi x. There may be no x such that psi of x gives you W star. So we need to figure out how to make a prediction in a way that's kernelized that doesn't directly access this infinite dimensional vector W star. So that's what this slide's about. So let's give it a try. So what's going to save us here is the representative theorem. So f of x is this inner product. Let's plug in what we know to be true about the W that optimizes our objective function, that W lives in the span of the data. So we can rewrite W as this linear combination, linearity to expand that out. And now we're in terms of inner products of these featurized input vectors. And how do we rewrite this? That's just kxix. Okay. So if we know how to compute our kernel between any arbitrary inputs, then we can also compute our prediction on a new x. Right? So whereas we started with an explicit exposure to w, which may be infinite dimensional, here we only have exposure to these kernel computations. And there's only n of them. Right? So this is how we have kernelized the prediction function. We've written it entirely in terms of these kernel evaluations.
So every data point in the training set has to be kept as part of the model.
Ooh, very nice observation. Every point in the training set shows up in this sum. So every time we want to make a prediction, we're going to have to access potentially every set in every element of the training set. That is correct. Except, when might we be able to ignore some input vectors? What if alpha I is 0? OK. If alpha I is 0, we don't need xi. Right? We can drop that from the sum. Guys, remember from our discussion on support vector machines? We had this whole set of slides at the end talking about exactly the situation of when these alpha i's are 0. Remember, it had to do with the margin condition? So yeah, it's a while ago. But for support vector machines, there's frankly, one of only 2 reasons to have gone through the whole Lagrangian duality was to understand that there are conditions under which alpha I can be 0. And if the example, the ith example, is kind of on the good side of the margin, right? So the margin is strictly less than 1, then the support vector, the corresponding coefficient is 0. Right? So any example that's kind of very easily classified by your prediction function will not show up in this sum, because it will have a coefficient of 0. So, so support vector machines work very nicely with kernelization exactly because we get sparsity in the alphas. So that it turns out you don't necessarily have to carry around all your x's to do your prediction. A little while later, we're going to kernelize ridge regression. There's no sparsity in the alphas in ridge regression. So if you want to make a prediction using your kernelized ridge regression, you're going to have to carry around all your input examples. Great. Good question. All right, so we kernelize the predictions. We've got to kernelize the rest of our generic objective function. Let's go with regularization now. So R of norm of W. How should we expand the norm of W? Norm is by definition square root of the inner product of the vector with itself. And then we know the form of W from the representer theorem. We plug in the form of W. We could expand this thing by linearity, and we get this. Now this should maybe look familiar depending on how recently you've done a lot of linear matrix algebra. But what if we replace this thing by Kij? That would be not the kernel function this time, but the kernel matrix. All right, so I did the kernel function there. But all right, so this was a simple substitution. And now I think, yeah, we'll define the kernel matrix K. We did this earlier, though, as having all the kernel evaluations between all pairs of I and j. So now we can sub in kxij with just the kernel matrix at ij. And if you don't immediately recognize it, you can work out pretty directly that this sum over ij is exactly this quadratic form in matrix notation, where K is the kernel matrix. So we get this very nice expression for the regularization of norm of W in terms of the kernel matrix in alpha as as follows. So even if W is infinite dimensional, we don't have to touch it directly because we could just do alpha transpose K alpha. All right. How about the predictions? So we already talked about predictions, but let's move towards the form that we're going to need for our objective function, where we need to make the predictions not just on our new point, but on all the training data points. So we're going to vectorize it to make it look nice and clean. So I've introduced a subscript on F, which is alpha. Alpha would be the parameters in this expansion we know exists from the representative theorem. So here we've just written out this expansion. And this we should recognize as, again, a matrix vector product like this. So this is just K alpha. So let me just recap this. So we have n input vectors, our n training vectors. We want to make when we make our objective function, we're going to, of course, have to find what our function predicts for each of those training vectors. That's f alpha x1 through f alpha xn. This is a vector of n numbers, column vector. And we can write this just as K alpha, so matrix vector multiplication. So subbing all this in, we can rewrite our original generalized objective in this very nice, concise way. So now we're optimizing over alpha. Originally, we were optimizing over W, but we recognized the solution has this form, so why don't we just optimize over alpha? W is 300 million dimensions. Alpha is 100,000 dimensions. Let's optimize over the lower dimensional parameterization. So minimize over alpha in Rn. N is how many training points we have. And this is our kind of objective function in matrix vector notation. OK. So note, there's no direct access to any individual psi xi. Everything's through the kernel matrix. All right, so that's successful kernelization of our generalized objective function. So we should be convinced, or convince yourself, that the SVM is a special case. The L2 regularized linear regression is a special case. Logistic regression would be a special case. Basically, anytime you have an L2 norm of W in your regularization, you're in good, and you have a linear prediction function, you're in good shape for kernelization with this in this form. All right. So SVM, you put in the K's, it looks like this. For ridge regression, I mean, if you want to go directly, the method is pretty straightforward. You take W, and you substitute in for W this expression. So every W gets replaced by this sum of this linear combination in terms of alphas. And then your objective function is in terms of alphas. That's kind of the recipe for kernelization of any specific thing. We did it in complete generality here, but you don't have to use this if you don't want to. You can just directly plug in this expansion for W in any objective function you have, and you'll get the kernelization. Okay. There's the kernelized ridge regression. All right. So how do we optimize this kernelized ridge regression? Is this fundamentally a different type of objective function than we've seen before for ridge regression? What kind of function is this of alpha? It's quadratic. It's quadratic. That's right. It's a convex quadratic. We'll show that K is positive definite. This would turn out to be a quadratic, convex quadratic. But as far as our methods, it's differentiable, so we can use gradient descent or stochastic gradient descent, for example. This also has a closed form solution, just in the exact same, using the exact same type of matrix algebra that we could use for finding the closed form solution for ridge regression. Okay. Great. Any questions on this? This is basically the recipe for kernelization. No need to go through duality. Just use the representative theorem, recognize that this is the form of the solution, plug in this expansion for W, and now you're in terms of alpha. If n is huge, if your training set is huge compared to your feature space, not a good thing to do. If your feature space is much bigger than your training set, good to go. Then it's recommended. All right, so I wanted to give you a little bit of a look at what things look like, the actual prediction functions look like when we use an RBF kernel, the Gaussian kernel, which is kind of the most popular. So I wrote down what the kernel function is again, between any 2 points. Okay, we talked about this already. So here I fixed a sigma. I took sigma equal to 1. Let's suppose we have 6 training examples. All right. So by the representative theorem, we know that the prediction function, that's the solution, will look like this. Right? That was the thing we did over here. So W is in the span of the data. The prediction functions is in the span of these kernel function evaluations. All right. So let's break this apart. So K is a function of 2 things. Xi is the training data point, and X is the new point. Right? So we're trying to figure out f of x. And to do that, we evaluate the kernel between xi and x for every I, for every training point I. So it's kind of like, here's a new point x. And we say, how similar, the kernel evaluation, how similar is x to x1, training point? How similar is it to x2? How similar is it to x3? And we get a bunch of numbers. Those are all these kernel evaluations. And then we take a weighted average of those similarities. Okay. So that's one way to think about it. Another way to think about it is that kxix, that's a function of x. And so the prediction function, as a function of x, is a linear combination of 6 other functions of x. Each function of x is a similarity function, which says, how similar is x to xi? So for any x, this function returns a similarity of x to a fixed xi. So let's draw those functions out. I made this graph a long time ago. You can see it's a little pixelated. Got pixelated with the years. So it's because I screenshot it on a really low resolution monitor, probably. So here's our kernel function centered at -6. So kx minus 6, it's symmetric, so that would be k minus 6x. It's a function of x. And of course, its peak is at -6. This is a -6. What would its value be there? Well, in this case, it should be 1. I must have a rescaling there. OK. And it decays as you get further away. And we have one of these, call them basis functions, centered around every training point. So the training points are just x, points in x. We'll say the input space is, the feature space is one-dimensional. All right. So a prediction function is some linear combination of these kernel bumps. For example, here's 2 examples. All right. And this visualization generalizes very nicely to high-dimensional spaces. So at least a little bit higher. So around any training point, you throw a little Gaussian bump, and you're taking linear combinations of these bumps in space. Okay. And yeah, so one point I really wanted to make is that whether you find this function, whether you find your alphas, find your f from a support vector machine or from regularized ridge regression, it's still going to have the same basic form by the representative theorem. It's still going to be this linear combination of the kernel function, these kernel basis functions, centered at your training points. Okay. So I wanted to make good on my claim that there is a feature vector representation corresponding to this RBF kernel, kind of just for fun. You never really use it, but I think it's quite interesting. So if we're going to work with these infinite dimensional feature spaces, we're going to need a little bit of a structure. So what do we need in this whole game? We need inner products. We need a norm connected to the inner products. And we need a projection theorem. We need to be able to take projections and know that projections reduce norm and this sort of thing. We need projections to exist. So basically, we need a Hilbert space. That's why we brought in that structure. And here's a Hilbert space that we will use for our infinite dimensional, that will host kind of our infinite dimensional feature space corresponding to the RBF kernel. It's called little L2, which you might have met before. It's a space of all real valued sequences, infinite sequences, that are square summable, all right? Finite infinite sum of squares. So theorem, this set of infinite sequences forms a Hilbert space if you define the inner product in what's probably the most natural way, which is just this kind of just the infinite extension of the usual dot product. All right. Okay. So the RBF kernel, I've written it in one dimension for simplicity here. So a kernel, just like we had on the slides with the kernel basis functions. So here's the claim, that the feature vector that would give rise to this kernel in one dimension has this form. It has the exponential, as you expected. So it's e to the negative x squared over 2, and then that piece is constant. That's just a function of x. And then in each of the coordinates, so n does not refer to the data set size here. This refers now to the coordinate of this infinite dimensional feature vector. Sorry for that overloading. So the nth entry of this infinite dimensional feature vector has this value. So the part depending on n is the 1 over square root of n factorial and the x to the n piece. All right. And you can prove by direct calculation that this gives rise to the kernel that's claimed. To be careful, you need to check that this is well defined. So does this even define a feature, an infinite sequence in L2? Yes, you can show fairly easily that this thing has a finite sum, which you need. And then just by working out the product of these two infinite, the inner product of these two infinite sequences, you can arrive back at the kernel. And that proves that we have found a feature vector representation of our Gaussian kernel. So it might be interesting if you want to experiment and look at what this feature vector, maybe the first 100 entries, the first 1,000 entries of this feature vector representation is for a typical, for this kernel, say, and a typical pair of input values. 1 and 0, 0, 0, 1 and negative 1, 10 and 1, these sorts of things. And maybe you can get some intuition on what these feature values look like. And the reason that's worthy, potentially, I actually haven't done it myself. I'd like to. I'd love to have you guys investigate this, is that as we keep discussing, the magnitude of the entries in the vector interact with the regularization that you end up using. And so it's important. It would be interesting to see where are the big entries in this feature vector and where are the small ones, because we expect the bigger entries to be regularized less and these sorts of things. Okay. All right. So the last piece we want to talk about is the kernel functions themselves. We've spoken about linear kernel and quadratic kernel and polynomial kernel and the RBF kernel. More generically, what functions can we use as kernels? So one way we can always get a kernel is if we start with an explicit feature vector and define the kernel as the inner product between the dot product of two feature vectors. So that's simple. Otherwise, we need a little bit of theory to help us. So this should be review. A real symmetric matrix M is called positive semi-definite if for any x, this form x transpose mx is greater than or equal to 0. All right. So some conditions for something to be positive semi-definite. All eigenvalues for a symmetric thing to be positive semi-definite, all eigenvalues are non-negative. It has a square root in the sense that you can factorize it into a matrix transpose times itself. But what we need really is this definition, which is that, so a kernel function, right, the kernel function itself, is called positive semi-definite if, for any finite set of points, if you evaluate the kernel matrix on that finite set of points, that matrix is positive semi-definite. Right? So we're defining a kernel function to be positive semi-definite if its kind of evaluation on any finite set of points gives you a PSD matrix. All right, so that's our direct method now to evaluate. Well, one sec. We need a theorem first. So a symmetric function kwx, potentially a kernel function, can be written as an inner product for some feature mapping if and only if that function is positive semi-definite. All right. So this is the theorem that gives this definition some legs. So if we start with the function k, and we can demonstrate that the function is positive semi-definite in this sense, then we know that it corresponds to this kind of an inner product for some inner product and some feature mapping psi. So if someone gives you a function, even if you have no idea, like RBF kernel might be a good idea. Someone gives you the RBF kernel function. Initially, you have no idea what the corresponding feature vector would be to give rise to that kernel function. But if you can show that that RBF kernel function is positive semi-definite, you know that such a psi exists. You don't even need to find it if you have a kernelized machine learning algorithm, machine learning objective. Okay. So that's kind of the bare hands way to figure out if your kernel is a legit, it's called a Mercer kernel, if you can write it in this way. Otherwise, what you can do is construct new kernels from old ones. So the sum of two kernels is a proper PSD kernel. You could scale them. You can multiply them pointwise. And of course, this is kind of a trivial version of an explicit inner product representation. You could think of f and w, f as your featurization, mapping to one dimension, and then you're just multiplying them. It's kind of a trivial inner product. So I've just put 4 kind of formulas here for creating new kernels from old, but there's whole chapters written on this sort of thing. How do you come up with a kernel that, how do you come up with new kernels and make sure that they are legitimately corresponding to feature vectors and inner products? Okay. All right, I think that's all I wanted to say about kernel methods, at least for now. Any questions? Might take some time to get comfortable with. We have there's a lab assignment, which we might make optional, but it lets you work through an actual kernelization and come up with plots that are very similar to these ones here. So you could actually see the prediction functions and with various kernels. You could use polynomial kernel, RBF kernel, and your algorithm for doing the machine learning is exactly the same. You just swap in a new kernel function corresponding to your new kernel. And then your prediction functions start to look dramatically different as you change kernels.